Okay, so Chem129, we're looking at, this is Chem129, we're looking at some of our molecular orbital theory stuff. We're going to start with number 14, which is an interesting heteronuclear diatomic problem. And you were specifically asking about, like, how do we think about this? So this is, the question is relatively straightforward. I hope the audio is coming through. This is that's okay. So 7.2, number 14, we're looking at HF. And so let me redraw this real quick so we can think about it together. We got our 1s. We've got our 2p and our 2s. And this is just asking about what's happening as these different orbitals are interacting with each other and what kind of happens. So what we have to do to think about this is we have to think about an s orbital on hydrogen as it comes towards the s, the p. I'm going to switch colors to try and make this easier to see. We're going to call this the pz. Then we're going to have our px. We're also going to have the py poking out of the board that I can't draw very well. And we're also going to have our 2s in here, which is not going to really interact, right? Since fluorine is highly electronegative, that 2s is going to be small. And so when I look at what's going to bump into this first, my 1s and my pz are going to bump into each other first. So I'm going to form some cylindrical, and that's not going to be the same as anything else. So I'm going to have my 1s and a 2p and a pz bump into each other. See ya? And that's going to give me something. If I try to sketch that on the bottom here, it's going to look like something like this. This chunk in the middle, this is going to be my shading. This chunk in the middle is going to get bigger because it's in that constructive interference case. And I'm going to have some like bigger bump there. It's going to have this kind of wonky shape, but it's going to have that cylindrical symmetry about it. So this is going to be a sigma. I don't have a great label for it. This is going to be like a sigma s dot p because it's a sigma bond made from an s orbital and a p orbital. And I'm going to have the same thing happen up here. For my sigma star. Or if my face was flipped, I'd have that destructive interference for that sigma star. And again, I wouldn't have a great label for it in terms of putting, like, it's nice when it's like p orbital, so it's a sigma p. This is like a sigma. We would just call it a sigma probably. We probably wouldn't put labels on it. My 2s is going to be sitting there kind of like not doing anything, not participating in bonding, not really doing any anti-bonding. And then my px and my py are also kind of not doing anything, not really bonding, not really anti-bonding. We call those situations they're not bonding, they're not anti-bonding. We call them non-bonding. And so again, it's a lot of definitions, it's a lot of terms. But this is you were asking mostly about this picture representation?
Yeah.
Okay.
And then also to answer the question here, like, how do you know if they participate in the creation of the sigma bonding with the hydrogen? Like the 2px, 2py, and 2pz.
So that's a geometry convention. So by convention, the axis, so technically, right, the p orbitals all look the same. They're just off by 90 degrees. So we just have to pick one that's going to bump first. And by convention, we always say bonding happens along the z-axis first. Okay. So we always pick the pz first. We just have to pick one of the three.
Yeah. And
just to be consistent with other people, we're just like, let's just always do pz first.
Okay, yeah, that makes sense.
Now, there's a better justification for that later on if you get into the mathematics. If you take Chem353 and do quantum mechanics, there's a really nice justification that has to do with the conversion of pz into spherical coordinate systems.
Okay.
What's your major?
Public health.
Don't worry about what I just said at all. It's just convention, it's pz. There's reasons behind it, but you're never going to need to know those reasons.
you're not.
It is a really cool class, though.
Okay.
Okay. So that's how we look at number 14. Questions about that before we pop over to number 6?
I don't think so.
Okay, so let's go ahead and take a look at number 6. Again, so this thinking is kind of similar to number 2. If you look back at number 2, where it's trying to get you to put together the different shapes.
Okay.
So this is an extension of that number 2 problem.
Is it
How do you put
the
a P?
LI or?
Oh, sorry, number 2
Number
from
three?
7.1.
Oh, number 2. Okay.
Number 2. I knew it was number 2, but it's number 2 from 7.1. Has us putting together s orbitals with p orbitals and figuring out these types of interactions.
Okay.
So if we look at number 6, what is number 6?
It's just like just like a basic MO diagram for F2. The only part that really I got all I figured out all the electron parts. The only thing that confused me was the effect on bond strength and.
Well, so the thing is, and this has been confusing a lot of people because you're not the only one, is what I'm saying.
Mm-hmm.
And it's because when we start clicking down the boxes, we forget to look back up at the top. So if you look back up at there, so what's it specifically asking for that problem? Right. So which part is this that you're asking about?
The bond strength versus.
Which letter is it?
Oh, it's D.
So scroll back up to D and read me exactly what D
Determine
says.
whether removing an electron would increase or decrease the bond strength and bond length.
So we're specifically removing an electron. And we're saying, will removing an electron decrease or increase the bond strength? Fluorine has 7 valence electrons, 5 p valence electrons. If I'm just looking at the p orbitals, it takes the non-mixing diamond pattern for its orbital pattern. I've got my sigma, my pi star, sigma star. I could label this is a sigma 2p, pi 2p, all of that, right? Now, if I'm removing an electron, bond order,
It's going to be affected.
it's going to be affected.
Okay, so then I would do it.
Bonding electrons minus anti-bonding electrons. So right now, this calculation is 6 minus 4 times a half. As we add or remove electrons, right, because we can think about this in a couple different ways. It's adding electrons to a bonding orbital or removing electrons from a bonding orbital. It's adding electrons to an antibonding orbital or removing electrons from an antibonding orbital. It feels like we have 4 different things we have to think about. But it's all just this. Right? All 4 of them are just, is this number getting bigger or smaller? Is this number getting bigger or smaller?
Okay.
So the problem said specifically, we are removing an electron. So I'm going to erase that electron.
So one less anti-bonding.
And I'm removing 1 anti-bonding electron, which means my subtraction part is getting smaller.
Which means the bond order would get higher.
Which means that it would
Increase
strength, decrease length.
Okay.
Right?
That
So
makes
it's not, and so this is one of the really important things in introducing molecular orbital theory, in that removing electrons, it now matters, well, where are you removing the electron from? Are you removing a bonding electron or an anti-bonding electron? We've never had a way to kind of conceptualize that thought before. We've always just been like, oh, we're just losing electrons. It's like, whoa, 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 from where? From where?
Okay. So what if it was like you're removing like 5 electrons? I doubt that would happen, but like.
So we're having, theoretically though, we can do this theoretically. So we've got our F2, right? This was originally F2.
Yeah.
And we want to go to F2 plus 5.
Yeah.
So the first 4 we would remove, I'm going to go ahead and draw this back in. Right, the first 4 we remove would all make this stronger because we'd be removing the anti-bonding electrons. The 5th one we remove would make it weaker because we're removing a bonding electron.
Yes.
Then just go through the calculation.
And we just calculate.
Okay.
Now, this gives us a little bit of a misconception of whether it's more stable or less stable.
Yeah.
We can say something about the bond being stronger and shorter, but fluorine is incredibly electronegative. So if we form F2+, right, get rid of that electron, F2 plus is going to be incredibly reactive because it's one electron away from getting that full valence shell. Well, it's just incredibly electronegative, and we're doing something to, it attracts electrons towards it very well. So F2 plus is going to be really reactive. It's going to pull electrons towards it. Yeah?
So when you remove an antibonding electron, the bond gets shorter, and it gets, or what, can you?
Yes. The bond order goes up, which means the bond strength goes up, and the bond length goes down. So bond order and bond strength are directly proportional. Bond length is inversely proportional. And the way I remember that, just like a little like classical fun picture thing, is long sticks are easier to break, short sticks are harder to break.
What does the get bigger, get smaller mean?
So as we lost an electron from the antibonding orbital, this antibonding piece that we were subtracting got bigger, or sorry, got smaller. Right. So our number of antibonding electrons got smaller because we lost an electron from pi star. We lost an antibonding electron. If this subtraction piece is smaller, then our calculation for bond order is going to be bigger because we're subtracting less.
Okay.
That bigger bond order means a stronger bond and a shorter bond.
Makes sense.
Generally.
When drawing it out, in class you showed us like the shortcut way versus like the more that way.
Yeah.
When you draw it that way, I get like a little I start getting kind of lost.
With all the dotted lines and everything?
Yeah.
Yeah.
Is it fine if we just continue to draw it this way?
If
or
you
is
include
it,
your labels, you're fine.
Okay, so you don't think like it'll hurt me down the road if I
The
draw
only
this way?
places where it gets a little bit tricky is if you lose count of your valence electrons and your p-valent. Like if you lose count of your electrons and how many electrons are going into the orbital, that's where you could get in trouble doing it that way. This way is like, here are my fluorine p electrons, here are my fluorine p electrons. I count them all up, I put them all in, and it keeps me keeping track of my electrons really well.
Okay, that makes a lot more sense then. If I it's like, okay.
Right.
Like
So
you have like for oxygen that we did in class. This is one oxygen molecule. This is another one, and then this is the combination stuff.
One oxygen atom, another oxygen atom, and then put together. And you're missing one of your dashes for your p orbitals there.
Okay. Wait. Where?
There should be 3 dashes for the p's.
Oh, okay.
Third dash there, same thing on the other
Okay.
side.
I'll scoot that over. Okay.
Now, yeah, and we won't get into the fact that the electrons should spread out a bit more and all of that to maximize multiplicity and get the ground state energy, but you're close enough with that. But it's 3 dashes and 3 dashes, so 6 things come together and make 6 things.
Okay, that makes sense. Thank you.
My 10 electrons become 10 electrons.
Okay.
And if I lose one, technically I can say I lose one. We don't really say it's like an F plus and an F coming together. We're losing the electron from the molecule. But we can think about it like, oh, one of our fluorines must have lost that electron. It's not the individual fluorine losing an electron. So I don't usually draw it that way unless I'm just doing it to keep track.
Okay. That makes sense. Thank you.
Like that. The last thing to talk about is titration curves. Yeah? Okay. Popping back a bit more, let me go ahead and erase this. And 124 was just doing their first titrations. And eventually you'll do full titration curves.
So it's 10. Oh my god, I'm so excited.
Where you measure, like rather than just measuring the endpoint, you measure every step along the way to see how the chemical compounds are changing over the entire titration process.
Is that like the bell curve thing?
No.
I must have just typed it wrong. Because that doesn't have 3, 4, 5.
Generally, this is the shape of our titration curve for a weak acid, strong base, monoprotic. If it was polyprotic, I'd have another jump and another jump and another jump. If it was weak base, it'd be starting high and going low. It'd just look like a mirror image of this thing. Right, but this is our titration curve generally.
It means to build up.
It always starts at a low pH,
What it means in terms of
has a little bit of a jump,
means
as we
that
get
it
into
has
a
to
little bit
go,
of a
like,
jump in the space
if
where
you
we
have,
can't
like,
really
singles,
calculate
it has to go to
because our
yeah.
x is small approximation is failing.
Exclusion principle.
And then we have our buffer region
It's like I learned this in AP Chem, but I forget.
where we have our weak
Um,
acid and our conjugate
I
base
think
both
it's like
present.
it can jump to a different level if it's strong enough. I would ask him about that though.
I did
Okay, so really quick, Pauli exclusion principle.
I did not. That's
What about it?
What is it?
The Pauli exclusion principle says you can't have two electrons that look exactly the same. So you can't have
I did like 2.5 years Chem total.
two electrons pointing up together like that.
Oh,
Because
yeah.
then they're being
Yeah.
specified by the same wave function.
Okay.
And you can see that by, wait, no, wrong thing, okay. I was gonna say, you can see that by setting up the Slater determinant and seeing if your electrons are inversible. But that's for 353.
I'm refusing against it.
You'll do it eventually. Wait, are you changing majors?
I might transfer schools.
To where?
Oregon State.
Oh, I was like, are you gonna go to Humboldt?
They
I'm
don't
not
have
making fun of Humboldt. That was an earlier conversation because we were talking about Humboldt becoming a Cal Poly. You can, I can. They're my colleagues. And I'm recording this, so I don't want anyone in the comments being like, "What'd you say about that?" This is not why I want to go viral. So we've got the buffer range. In the buffer range, in the buffer range, we've got some of our conjugate base, and we still have our weak acid both present. Over here, our initial point, we only have HA, we only have weak acid. Right? Then we get into this other region where that curve is happening and our x is small approximation is failing. We can't really do the calculation. And then we've got another part here where the curve is going and we can't really do our approximation. And we've got this one spot, it's technically a range around this spot where we can do it, but we only do it for one spot where we only have A minus. And right, we see this kind of conversion of the material, and I'm kind of talking through the entire concept of the titration curve, not just doing the sketch by itself. We kind of see this process across the entire thing where if we're looking at HA and A minus, it's 100% HA and it's 0% A minus. And we have a spot where we can't calculate it. Right here at the midpoint,
How?
we would have 50-50.
Yes. That's stupid. I would ask.
Right, we'd have 50-50. In this whole buffer region, we'd have like this switching from approximately, I'm just going to do approximate, right? This is approximate 90-10, right? It's technically 91 to 9, something like that. I can't remember the exact calculation, but we've got that approximately. And then over here at the other end, it's going to be approximately 1090.
I think I see your problem. Okay, wait, let me try this real quick. I think I figured it out.
Then, when we get exactly to this midpoint, sorry, to the equivalence point, it's 0, 100.
So there's only more questions.
Right, so our acid gets converted completely to conjugate base. And so we go from 100% acid, if we add the right amount of strong base, we go to 100% conjugate base. And as we get close to that point, as our weak acid starts to completely run out, that's where we see the pH start to skyrocket up and we get that steep part. I've never done it this way. I kind of liked it, like this. Where I've got this like kind of like this progression percentage on the bottom too.
Can we do it with the numbers in the exam?
Really?
Is that
Oh, yeah.
fine, or
Yeah, sure.
I
I just don't remember
We
them.
have not done that.
it's
Oh, yeah.
So the things that we usually ask is like, what's the midpoint, what's the equivalent, what's the midpoint volume in pH and what's the equivalence point volume? Is that those are the numbers you want?
Can
Okay.
you help with that? Just to
Yeah.
try to find the
So,
buffer range.
yeah, so can I see that copy of the exam real quick?
If you don't get it,
Thank you, because I don't remember the
For
numbers.
some reason it clicks for me.
I know, right? Shocking. Okay, so we've got this situation. Do you know if you had version A or version B, or can I just do it for either?
I don't know. Sorry.
That's okay. It's on the front page. Did you go to 10.95 or 9.95 for your target pH?
9.95.
You have the other version. Give me your numbers.
Okay, this problem we will be making 350 mils of 0.052 molarity caps buffer with a target pH
Was it
of 9.
0.052?
Yeah, 0.052.
Oh, low concentration. Okay. Okay.
Target pH of 9.95 with 1 molarity of strong.
Okay.
I always guess wrong
Pretty good.
Is it acting like an acid or a base? It's an acid, right?
Yes.
So this will be 1 molarity OH minus. What's its pKa?
10.41.
What does that mean? Circle?
Okay, so what's the easy thing that you know right away?
So what's wrong about that? That looks right to me.
Why? Is it the max of the buffer range or at times? Or no,
No, the easiest thing.
M1V1.
Easier than that.
Yeah,
That's right.
The pKa equals pH, right?
At the
Start reaction.
Which is, or at the midpoint.
at the midpoint. Right, so let's go ahead, let's explain that again. Let's do some math to prove that. But I know the pH at the midpoint is 10.41. That's the thing that's always true. And so we can see that pretty easily in the Henderson-Hasselbalch equation, because we're going to have pH is equal to pKa plus log of like 50% divided by 50%. Right, so we're going to end up with the log of 1. This part just goes to 0. And we just get pH equals pKa. That always happens at the midpoint. Every midpoint that happens because the ratio, the midpoint is always when you're half-half. And so the ratio inside of the log is always equal to 1. And the log of 1 is always equal to 0. So that's why the midpoint pH is always the easiest point to find. So that gets us the pH there, and it usually doesn't ask us other things besides the pH at the midpoint. So that gets us the pH at the midpoint. It's just pKa. Now we say, okay, well, I have this whole thing that's like 100%, 50%, 100%. Ooh, I'm bumping into the camera. So what's the total moles of my system? What would if I put this into moles, what would my 100% be?
There's 6 points each.
Yeah, these are 6 points.
That's wild.
I
don't know.
Total concentration times total volume. So I just do 0.052 times 350. And this would be
12 at 18, yeah.
18.2 millimoles.
That's wild.
Right?
Okay.
So all I did was I multiplied these two numbers. I did my total volume times my total concentration. That gets me my 100% of moles. So when I do the correct amount of stoichiometry, this is going to be 18.2 millimoles over here, the other 100%. And then my 50s are going to be 18.2 divided by 2. These are going to be 9.1 each. Now the question is, how do I get 18.2 millimoles to react? What do I need to add to get 18.2 millimoles of acid to react?
The OH.
Yeah, how much OH? Well, let's think about this. How many millimoles of OH to get it all to react?
Just M1V1?
Easier than that. We're going to get to M1V1 in a moment. If I started with 18.2 millimoles of acid, how much base do I need to react it all?
18.2.
Yeah. Hey, yeah. So it's just I made it too easy, maybe. Sometimes I try to ask easier questions, and people are like, no, you got to do Henderson-Hasselbalch. I'm like, oh, not yet. Right? So we know we need to add 18.2 millimoles of this. If it's 1 molar OH, you're just going to do to get to this point, let me switch colors to be consistent. This is going to be 18.2 millimoles equals molarity of strong base, volume of strong base. But guess what? My molarity is equal to 1. So this just becomes 18.2 milliliters. Right, and this is part of the reason why we often, as chemists, if we have choices in what concentration to use, we like to use a concentration of 1, because then the moles we calculate is the liters. And it's like super easy, because you're just multiplying or dividing by 1. Which is why it looks like a coincidence that it's 18.2 and 18.2, but that's because we're just dividing by 1. Right, and so technically, I did sneak in a little M1, V1, M2, V2 there, right? Or, sorry, the way I like to say is molarity of weak acid, volume of weak acid equal to molarity of strong base, volume of strong base at the equivalence point only because that's the definition of the equivalence point. Don't use the dilution equation. I'm looking at my 124 students. You would. Right, so this is going to be my molarity of weak acid times my volume of weak acid is where I got that 18.2. And then that's equal to my molarity of strong base times my volume of strong base if I'm at the equivalence point. That works. Not because M1, V1, M2, V2 generally works, but it's because at the equivalence point, my moles of weak acid equal my moles of strong base. So I do calculate moles equals to moles. Right? That's the equivalence point. The moles are equal to each other. So then how do I find the midpoint volume from this? Yeah, midpoint's halfway. So I just take that 18.2, I divide it by 2, and I get 9.1 milliliters to the midpoint. Typically when I do this, like you've seen me do this in class before, to calculate those three, to calculate the 10.41, the 9.1, and the 18.2, I can usually do that in less than 2 minutes. Right? Because it's multiply these numbers, divide by that gets me that, divided by 2, that gets me that, that's just the pKa. I could probably do it in like 45 seconds if I was really pushing it. Right, so it's supposed to be a relatively quick question that then sets up the framework for how we think about the rest. So, what was your target pH?
9.95.
This is an art exam.
9.95 is going to be like here.
Whoa, it's so different.
So you know your volume has to be between 0 and 9.1 for the amount of base you're adding. It's probably going to be like 4 or 5 milliliters of base to be the right answer. To get the exact right answer, we need to do the Henderson-Hasselbalch equation and the stoichiometry. But I can eyeball it and say, look, it's somewhere, it's probably like halfway between 0 and 9. It's probably like 4.5 mils. Approximately. Right, and this, so that gives us this context of how we can think about the rest of the problem to get like, to tell if we're doing a calculation properly or improperly. So if you ended up calculating a volume that was like, I had some students that did the titration curve correctly and then calculated 67 milliliters for the base they needed. And I'm like, dude, that's like way over there on the titration curve. They're like, oh yeah, that doesn't make sense. But they didn't realize it until after they turned it in because they just got used to punching everything into their calculators without thinking about the system they're trying to represent and the context of the math. And I've been trying to stress that context of the math a lot.
No, that's his grading.
Oh.
Don't mind this.
Oh,
I ran out of time.
Yeah. I just want to see how other people do their grading.
He just scribbles pink all over it.
Yeah, it looks like
I don't really know what it means.
Sounds like my grading.
How do I calculate the ends of the buffer range?
Okay, so the ends of the buffer range, there's the silly shortcut, which I've been trying to not tell people about too much. And then there's the proper way to do it. But like, always kind of comes out the same.
I think you always have a shortcut for everything.
1/11, 10/11.
1/11?
Well, let's do it with this. Let's do it with the Henderson-Hasselbalch equation.
Okay.
So the buffer capacity is 9/11. Don't forget that.
Okay.
No, I'll explain. Right, this is a fun kind of like math quirk, and I've definitely talked about this before, but I don't like to do it too much. I'm doing it on video right now, so I gotta be careful. But like, if we do our calculation with the Henderson-Hasselbalch equation, we know that the beginning of the buffer range is going to be at 9.41. Yeah. So I go ahead and I say 9.41 is equal to 10.41 plus log of A minus over HA. And then I can say, you know what, I'm going to do some stoichiometry here. So I'm just going to say this is going to be the ratio, this is going to be my stoich. I'm going to flip the board because I ran out of space and do some stoichiometry on the other side, and then we'll come back to it. My stoichiometry that I have to do. Hey, there's stoichiometry on this side from another class. So the stoichiometry that we need to do, right, and this is like, I have done enough practice that I could jump straight to doing the stoichiometry in Henderson-Hasselbalch, slam it all together and just like crank it. But let's think about the stoichiometry. Our stoichiometry is HA plus OH minus goes to A minus plus H2O. I know I'm starting with 18, was it 18.2? That was 18.2 here. I'm adding some moles of OH minus. I'm starting with a 0 there. I don't really care about the water. This is my start. I'm going to react. And then I'm going to have some endpoint. I'm going to put end in quotes because we know it's not really the end. We have to do equilibrium as well. You good?
Yeah.
Okay. Great. I know we're not at the equivalence point yet. Right? Yes, scoot over. I know we're not at the equivalence point yet. So I know my hydroxide is going to be limiting. So I'm going to have minus some moles, plus some moles to do my stoichiometry.
Thank you.
You bet. See ya. This is going to be some number of moles here. Right, 0 plus n, and I could put the OH minus on all of these, right? But since I've only got one variable, I kind of get lazy with that a little bit. This goes to 0, because all of my strong base is used up. This becomes 18.2 minus that moles. Right, and this makes sense, because every bit of strong base I add uses up some of my weak acid and converts it to conjugate base. Over and over and over again. Every bit I add. So if I added 0.1 moles of base, it uses up 0.1 moles of acid, makes 1.1 moles of conjugate base. Right, that would happen over and over again. And so we're going to do it until we add n moles. I can then take this, there were two tricks that we used. If we have a ratio of A minus to HA in terms of concentration, I can look at that as A minus over volume total. Sorry, I can look at this as moles of A minus over volume total divided by moles of HA over volume total. And that just is equal to moles of A minus over moles of HA. Right, this was one of our shortcuts, which was if we've got a ratio of concentrations, it's the same as a ratio of moles as long as the total volume is the same. So I can say, look, my A minus, this is going to be my moles of OH minus added, this number here, divided by my moles of OH minus, that's going to be my 18.2 minus moles of OH minus. So I'm going to plug that into my Henderson-Hasselbalch for my stoichiometry. If we were doing a different thing, if we were doing a weak base with strong acid, we would do something else. If we were doing, there's different stoichiometries. If we had a buffer, we were adding strong acid, that wouldn't be 0, we'd be doing something else, right? There's a lot of different stoichiometry we can do. Do the stoichiometry, then plug it into Henderson-Hasselbalch. Using our two shortcuts. Shortcut number 1 is x is small twice. Shortcut number 2 is ratio of concentrations in the same total volume. So then I am going to end up with my moles over 18.1 minus my moles. And if I solve this out, 9.41 minus 10 to the power of 10 gives me 0.1 is equal to n over 18.1 minus n.
Goodness gracious, sorry.
I'm going to do a little bit of mathematical rearrangement. I'm going to multiply this over, divide that over, and I'm going to get 18.1 equals 11n. Right, because it's 10 plus 1, and then I'm going to get 18.1 times 1/11 equals NOOH minus. 1/11 of my equivalence point is always here. Because we're using the definition of buffer capacity, or buffer range of plus or minus pKa plus or minus 1, the math always works out to be 1/11.
So we would just divide it by 11 to get the minimum, that buffer range, and then the other side, you said it was
Always ends up being 10/11.
times 10.
Always ends up being 10/11. Now, I don't teach this shortcut in the class because I don't want people to just be like, oh, I'm just going to do 10/11, 1/11. I want to see that they understand like why that's true, because I ask other points inside here as well. But my hope is that everyone's been doing enough practice. And I actually, someone in during lecture actually said, wait, is it always 1/11? And I went, yeah. And they're like, oh, okay. And like, I don't think most of class picked up on that. But my hope is that you're doing enough practice and you're seeing it often enough that you're like, oh yeah, there's a pattern to this, right? The essence of chemistry, in my opinion, is just pattern recognition. We see patterns in the periodic table. We see the patterns in the types of reactions. We see patterns in the stoichiometry. We see patterns in the buffer, in the titrations in the buffer capacity. So if it's always 1/11 to 10/11, what happens when you take the difference between those two? 10/11 minus 1/11?
The midpoint?
Ooh,
Or the
buffer range.
buffer range?
Sorry, buffer capacity. Is 10/11 minus 1/11?
Oh, I see.
Would it be, no, it wouldn't be, it would be factor of 9.
9/11.
9/11.
Yep. 9/11 of your equivalence point is your capacity.